afternoon, everyone. I'm Siham Al Shanti. I'm a postdoctoral fellow at the University of New Mexico. I present today research titled A Design Framework for 3D Printed Polymer Concrete. I worked on this research with my colleague, Dr. Daniel Hiras Mortia, under the supervision of Dr. Mahmoud Rida Taha. So in this presentation, I'll start with an objective and then a brief introduction to polymer concrete. I believe you all had it so. And then I will present the 3D printed polymer concrete by design framework, and all the other bullet points are about designing polymer concrete for 3D printing, and then I will conclude with a conclusion and the future work. So our objective in this research was to establish a comprehensive framework by integrating experimental methods and computational simulation to develop a 3D printed polymer concrete by both characterizing the material to have it in the best performance for a 3D printed structure. So you now all know that polymer concrete could partially replace cement or fully replace cement. Our interest is to fully replace cement, so we are using resin and hardener and aggregates. So we have three phases: the polymer phase, the filler phase, and the voids in between them. And what gives polymer concrete is a strong performance and high durability. It's the chemical bond between the polymer and the aggregate. So for 3D printing polymer concrete, we have to follow some steps. The first one is start by designing a mix design, and then subject it to a pre-Menelier assessment and 3D printability assessment. After that, measure its rheological and early age properties and design simulation. So we will have a full-scale 3D printed structure. So how to design a polymer concrete mix design? It's a composite, so we could use the rule of mixture to do it, the upper bound of the rule of mixture, and we can see from the rule of mixture that the properties of the composite will depend on the volume fraction and the properties of the polymer itself and the aggregate itself. So for example, we can use a polymer with a density of 600 kilogram per cubic meter up to 2,500, and we can use a volume fraction from 10% up to 100%, and the corresponding aggregate fraction too. So in our research, we narrowed down these parameters, and we focused on the aggregate to polymer ratio and the rheology modifier content for 3D printing. And for rheology modifier, we have used fumed silica. So based on that, we have designed 17 polymer concrete mixes with a varying polymer weight. The maximum is 19.9. Of course, you would say that this is not a polymer concrete when we have no aggregate, but it's for terminologies. And for the lowest is 4.3. And then before 3D printing, so to see their potential for 3D printing, we followed the procedure that is usually used in literature, which is the slump and slump flow. Of course, we will start by visual assessment to check if it's dry to fluid, and we can, by trial and error, adjust the dosage of fumed silica. And then the slump, it will give us an indication of the structural build-up during 3D printing, and the slump flow, which will give us an indication of pumpability and extrudability. So a good 3D printed mix should have a slump between 4 and 8 millimeter. We agreed on that. And a slump flow between 150 to 190 millimeters. So it's on literature, and that's based on our experience with the 3D printing polymer concrete. So based on our mix designs, 4 only out of the 17 designed mixes fell within the acceptable printability range. However, I need to note here that all these red mixes could fit into the box if we modify the rheological modifier content and we fine-tune the mix with other polymer types. But 4 were sufficient for our research process. So the next step comes where we want to examine the polymer concrete for 3D printability. So we started by defining the 3D printing parameter, and to do that, we selected different printing speeds, 50, 100, 150, and different extrusion speeds, and we 3D printed an L shape. This is the design shape that we 3D printed, And we measure the width and the length of it. So we got a ratio of the printed filament, the actual one, and the ideal designed one. A ratio equals to 1 means that I have a shape stability, above 1 over extrusion, below 1 it's under extrusion. So we had a plot between the different mixes, the 4 mixes that fit into the box, and we selected their we can select their printing speed and extrusion speed where they are closer to 1. The next 3D printability assessment is the printability window. And the printability window is how long the mix could be 3D printable and show that without any signs of segregation, clocking, disruption, or breakage. So for the 3 mixes, we kept printing at different intervals. And we can see as we are increasing the polymer dosage, the printability window has extended. That gives another benefit for polymer concrete, that we could fine-tune the mix to reach to a printability window that is for a specific type of application. Because usually 3D printing should be done really quick before the mix hardens. So for polymer concrete, we could extend the printability window or reduce it. So for the lowest polymer weight, which is 15%, we had 60 minutes. For 21, we had 2 hours. And for 29, we had 3 hours printability window. And we also noticed that the shape of the filament decreases with time until it reached the optimal width that we designed for, which is the nozzle diameter, which is a 20 millimeter. And after that, it goes to the distortion. Okay, for the buildability, we examined the buildability by 3D printing layers above each other. So if we showed any sign of a plastic deformation or elastic buckling, that's a type of failure that is not considered. So you can see in the above video, this is a plastic deformation. We were 3D printing, and then we had a permanent deformation to the structure. So those are types of failure that those mixes were excluded. And they happened at a high polymer weight, 47 and 59 polymer weight %. So all the 3 mixes that printed 10 layers without failing considered successful, and they went to the other buildability testing, which is measuring the deformation from a preset height. So we recorded a 20-hour video, and then by image processing, we calculated the deformation from the height, and we could see increasing the polymer content, which is mix 3, had the highest deformation compared to mix 1, but all of them were within the range of the traditional cement concrete, even below the traditional cement concrete, like from 6% to 11%. And here are the references for the papers where they reported the same testing for traditional cement concrete. After that, here comes step 3, which is the rheological properties and early age. So we did a rheometer testing by pre-shearing to avoid any shear history. We round it up to 100, and we round it back down to 0. And then we got, this is the typical behavior of polymer concrete as in rheological testing, which is a hysteresis loop. The area between the 2 curves is the thixotropy, and the maximum stress is the static yield stress, the stress that requires for the material to initiate the flow. And the y-intercept is the dynamic yield stress, is to maintain the flow after extrusion. So we could see also increasing the polymer content reduce the static yield stress, the dynamic yield stress, and the thixotropy. However, all of them were within the range for 3D printing polymer concrete and another cement materials. So here is the most important slides to me, because this summarize all the previous work that we have done to judge the mixes. So in the future, if we have another polymer concrete mix, we will not do printability testing or any slump and slump flow. We will directly do a rheological testing, and these are the boundaries of the polymer concrete. If it's too fluid, for example, we could increase the fumed silica, or we could reduce the polymer weight. If it's too stiff, we could increase the polymer weight, and so on. So those are the ranges. For example, the static yield stress from 700 to 1,500, and for the dynamic, 200 to 500, and so on. For the early age properties, we could use the unconfined compression test and the direct shear test at early ages. I mean from 0 minutes to 120 minutes to measure how the stiffness and the cohesion and the angle of friction evaluate like changes with time. So this gives us an indication of the structural build-up and the buildability of the mix. So it can carry its own weight, which is very important for 3D printing. So here are some results. You can see at time 0 minutes, we have a low shear stress. When we increase the time, the shear stress is increasing. The same for cohesion and the friction angle. We could see that there is a bilinear relationship, and that point where the two lines intersect, it's where the polymer concrete starts polymerization and it started to harden. So we are no longer can print it, but now it can carry additional weights. For the elastic modulus is the same, it's changing and it's up to 30 minutes. So it depends on the polymer type we are using. After that, we go to the structural capacity, which is the compressive strength, increasing the polymer weight, reduce the compressive strength at early ages. However, after 7 days, the lowest compressive strength was around 6,000 psi, which is similar to high strength concrete at 28 days. For the elastic modulus, we have a very low elastic modulus, and it's considered a lightweight material for construction. And those two properties helps polymer concrete in vibration attenuation applications where we need it in seismic and earthquakes applications. We fed all the discussed data into a finite element model. Wait, let me play the video. Okay. Into a finite element model, and the finite element model could give us the stress contour and the displacement contour. So the finite element model predicted that we will have a local buckling at the 10th layer. So this could help us to predict failure prior to establishing a full-scale 3D printed structure. And then you do a full-scale 3D printed structure. This is using a robotic arm. This is polymer concrete. And here, by using gantry, and this structure is for acoustic black hole thing I did my PhD dissertation on. So it attenuates vibrational waves. So it's used in sensors. And now you all know the applications of 3D printed polymer concrete. We could use it in precast electrical boxes, architectural facades, tanks, manholes, vibration damping material, and in other, like in pipes and other precasted elements. So as a conclusion, polymer concrete can lead the way as emerging technology in the construction field. To have a next generation 3D printed polymer concrete, we need to follow steps by polymer concrete mix design, pre-mineral assessment, rheological early age properties, hardened properties, and then a full-scale 3D printed structure. We could optimize polymer concrete mix, and that's the beautiful thing about it, that we could play with the properties, not like the cement concrete, and the printability region should fill within a range, and it would give us a practical guideline for the future polymer concretes. And here is a further reads of the published articles of us about 3D printed polymer concrete you could read. And here are some publications of Dr. Taha research team, our team, a picture of us. And thank you for all sponsoring organization and for Next for funding this research. Any questions?